Welcome back to another exciting episode of our video compressor app series. So if you are new here, my name is Izzy and I'm super glad you are joining us today. On this channel, we build real-world software engineering projects from scratch in a step-by-step approach so that you can learn by actually doing. Don't forget to hit that subscribe button, give this video a thumbs up and turn on the notifications bell so you never miss an update. To all my returning fans, thank you so much for being part of this journey. Your likes, comments and shares means the world to me. Keep showing love and let's keep building together. Now let's have a quick recap. In part 1, we set the foundation. We talked about what a video compressor does, why it is useful. We planned our architecture and we also demonstrated how the finished version of our app works. Then in part 2, we scaffolded both the front-end and back-end projects. We created the Spring Boot backend with all the necessary configurations, including setting up our application properties file, initializing dependencies, and structuring our package layout. On the front-end side, we built the HTML and CSS UI. We configured Webpack and got everything ready to start handling video uploads and processing. So now in part 3, we are diving deep into the meat of the application. We are going to be implementing the backend logic that actually makes the magic happen. First, we will walk through all the essential configuration files, including WebSocket configuration, course config, and multimedia file handling set. This is to make sure our app can communicate and process files smoothly. We will then look at how to handle file uploads securely and efficiently, how to manage background processes using multi-threading, and also implement a robust backend validation to ensure only valid videos are processed. We will also look at FFmpeg, which is the powerful open source tool we will use to compress videos right inside our Spring Boot app. I will show you how to integrate FFmpeg, execute compression commands, monitor progress in real time using WebSockets, and even allow our users to cancel ongoing compression tasks if needed. Yes, in this video, we are going to cover everything related to the backend of our video compressor from setup to execution. By the end of this video, our app will be fully functional on the backend. Having said this, let's jump into part 3 of building our own custom video compressor. We are going to start creating all the necessary configuration classes. The first configuration class we'll create is the course config class. It will serve as a Spring configuration class that defines course policies for our backend. It is going to allow the front end, which will be running on a different port, which is going to be mainly localhost 2020, to securely communicate with our backend server. Now let's quickly implement the course configuration that we'll be needing for this project. Alright, presently we have done the following configurations. So we have enabled course for all endpoints with specific settings, as you can see. We are also allowing all HTTP methods such as get, post, delete, and put. That is why we are putting a star here. So we also allowed all headers, and we are also allowing credentials such as cookies, authorization headers to be included in cross-origin requests. Then we set the pre-flight request to be cached for 1 hour. In summary, this configuration file will be in charge of allowing cross-origin requests from HTTP localhost 2020 to access the Spring Boot backend. So it is designed to support all methods and headers while allowing credentials and also caching pre-flight responses for better performance. Our front end is going to be running on localhost 2020. So any request coming from the front end will not have issues getting to the backend. So as we have already handled course. The second configuration class that we are going to be creating is the multi-path config class, which is a Spring configuration class that will be charged with the responsibilities of customizing the settings for handling file uploads in our video compressor app. Now let me quickly implement the necessary configurations for this class. Right now, we have configured the maximum file and request size for our upload. As you can see now, we have configured the maximum file and request size for our file upload. So we set the maximum file size to 2 gigabytes, and we are also setting the maximum request size to 2 gigabytes also. In summary, this configuration implementation is going to allow a user to upload a video file of up to 2 gig in size, and also it limits the total request size for uploads to 2 gig. So this will enable large file transfers in our video compressor application. We can increase this upload file size to maybe 10 gig or more, but for this tutorial I'm just using 2 gig. The next thing we are going to do, so we are going to specify the directory where our compressed video files will be stored. All right, so go to the application.properties, and in my own case I have chosen to specify mine on the file system at /user/desktop/download/compressed videos. So this is where all compressed videos will be outputted for me. So you can specify any location that you would prefer videos to be outputted for you during compression. In summary, this setting will define where the application should save compressed video files. Now, the third configuration class that we are going to create will be for WebSocket. We are going to call it WebSocket config. This WebSocket config class is going to act as a Spring configuration class that will set up WebSocket communication using Stomp messaging for real-time updates in our video compressor application. The main reason why we need WebSockets is to be able to send real-time progress of a video that is being compressed to the client side. We are using this progress response from the backend to update our progress bar in the front end real time. So when the video is being compressed, we want to be getting real-time updates of the video compression in bits, all right? And we want to be sending these bits to the front end, and this bit will be used to construct the progress bar, so we know exactly when a video compression process will complete. So let me quickly implement the necessary configurations for this WebSocket class. As you can see here, and as I've said earlier on, we have specified our WebSocket endpoint, which is going to be /progress, and this is where clients will connect to receive messages. We have also set the allowed origin to HTTP localhost 2020 because that is where our client side will be running on. We have also used our soft.js fallback options for broader browser compatibility. Then we are using a simple in-memory broker for our destination, starting with /topic, and all client messages coming to the server will be prefixed with /app. In summary, this configuration class will allow our client application, which will be running on port 2020, to connect seamlessly to the server via WebSocket to receive real-time video compression updates. Now, the next thing we need to do is to create our WebSocket service class. So we are going to create an interface called WebSocket service, and then we will also create an implementation class for our WebSocket interface. So we are going to have a method that will be in charge of sending real-time video compression progress updates, and the method is going to take custom response objects that will contain the compression progress and also some other details that are necessary. Now let me quickly implement these. So we annotated this class, as you can see, with active service because this class will act as a Spring component, and it is also used to show a class that handles business logic, because this class will be handling a business logic here. So this class sends real-time compression progress updates to connected WebSocket clients. All right. So we are also using a simp messaging template to send messages over WebSocket. And then we have our core functionality here, which is going to be in charge of sending progress updates to all subscribers of the /topic/update progress channel. All right. So in summary, what this service does is to broadcast our video compression progress updates to clients in real time using WebSocket messaging. Let's also create a controller class for our WebSocket implementations. You can see that we've annotated our controller class with attribute controller components, which is typically used to handle WebSocket related HTTP requests. Now, this controller will act as a bridge between our application logic and the WebSocket service. So we have also injected our WebSocket service to send real-time compression progress updates to clients. So in summary, this controller provides a method to trigger real-time compression progress updates via WebSocket using our WebSocket service that we have already implemented. So next, we are going to create a service called Video Compression Executor Service. And this Video Compression Executor Service class is going to act as the main executor that takes a video upload, compresses it using FFmpeg, tracks progress, handles errors, and returns a structured result. All of this will happen while ensuring resource cleanup and system stability. This class is going to be in charge of so many operations, though we are going to make sure that concerns are properly separated and that methods are broken down into smaller functions. Because while we are trying to achieve functionalities, we must also strive to follow best practices. So this class will oversee the following responsibilities. The first one is reading configuration values, then handling a full lifecycle of a video compression tasks by validating input video, preparing temporary and output directories, saving the uploaded file, analyzing video duration using FFmpeg, starting FFmpeg compression process, tracking compression progress asynchronously, waiting for completion process of or throwing a timeout error, validating output file after compression, returning a structured success response, cleaning up temporary files and job references, managing errors and resources, ensuring cleanup of temporary files and job data even on failure, enforcing timeout for long-running completion tasks, and also throwing meaningful exceptions on failure. So this particular service is going to be in charge of the main compression operation. All right. Now, having said that, let's get started with the implementation processes. So this is what I want to do. So I will write the implementations and then I will come back to explain in details what the code is designed for. All right. So let's get started. Firstly, let's inject some configuration details here. Now, let me explain this. We have attribute value, then you see this $sign, we say compressed.videos.folder, then we have a field called a private string compressed folder. So this line is going to inject the value of the property compressed.videos.folder, which is from our application of properties files into this field. As you know already that we already set our compressed.video.folders in our application of properties file. So then this folder part will be used to store the compressed video files. Then we have another property here, which is attribute value. Then there is $sign. Then there is compression.timer.minute, which is 60. All right. So then we have a field called a private int compression timeout. Now this line sets the timeout for compression in minutes. So if we don't already specify the property in the configuration file, it defaults to 60. It defaults to 60, all right, which is 60 minutes. That's 1 hour. So this is very useful for setting time limits on long-running tasks like our own video compression process. So what we are saying here is that we want each video compression process to last up to 60 minutes, all right. So we are expecting that a video compression should be completed within 60 minutes. If not, there should be a timer. The process should time out. All right. So I'm setting this just for this tutorial. You can decide to reduce your own or increase your own. Now we are going to create a method called compress video. which is going to take an uploaded video, which will be a multi-part file. All right. So then it will take the uploaded video, it will compress it and return a success response. All right, so right here we have created a success response, as you can see here. Now the next thing we need to do is to validate the video input. We are going to create a method that will handle a video file input validations. Now, this method is going to ensure that the file that the user selects for compression is actually a video and not an image or something else. The method is also ensuring that the file to be compressed does not exceed 2 gig. And now, like I said earlier on, in order to follow best practices, we will create a dedicated service that will be in charge of handling all validations. And then we are going to move this functionality for validating input there. So we will then inject the validation service into our video compression executor service. Now, having done that, let's create another method that will ensure that the output directory for storing compressed videos exists. Now, this is what this method does. If the directory does not already exist, this method will create it. So this method will be in charge of automatically creating an output directory for users when they are compressing videos. So if the directory does not already exist in the system, this method will create and return it. In order to continue following best practice, we are going to create a utility service. Then we'll move this method here and then we'll inject the method from the utility service into our video compression executor service to keep everything clean and simple. Now, having done that, let's create another method. We are going to create another method that checks whether there is enough disk space in the target directory to safely compress a video. Now, this method will ensure that the folder where the compressed video will be saved has at least twice the size of the input video file available, and it will throw an error if not. Alright, so video compression often needs temporary space for processing. Having extra space avoids failures during encoding or intermediate file creation. So for instance, if a video is 500 MB, this method is going to check if at least 1 gig is free in the in the output folder. So if not, it throws an exception. Okay, now we are going to move this method into the validation service and then inject it into our video compression executor service. Alright, so let's create another method. We are going to create another method that will be in charge of generating a unique and safe temporary file path for storing compressed videos. So let's quickly implement that. Now we have created a method called create temporary file path, which will help us generate a unique and safe temporary file path. So we started by sanitizing the file name, and then we generated a unique UUID to avoid naming conflicts. So we are then returning a constructed and formatted new file path in the folder passed to the method. Alright, so in summary, this method is designed to create a unique and secure temporary file path for saving compressed videos. So we have moved this method into our utility service, and also we have injected it into our video compression executor service, as you can see. So having done that, let's now implement another method that we handle the generation of a clean and organized output file path for saving the final compressed video. So let's also quickly implement it. Right here, we started by sanitizing the original file name. Alright, that is by replacing our non-alphanumeric characters with underscores. We then constructed a new file path in the specified folder with the prefix compressed underscore. Alright, so which means that every new file will be starting with a compressed underscore. So in summary, this method has created a safe and organized file path for the final compressed video file, and this method should also be in the utility service. Now we're going to create another method that saves an uploaded file to a specified temporary location and also validates the save operation. So let's dive into it first, then I'll come back to explain it. Right here, as you can see, we started by transferring the uploaded file to the given temporary path. We then checked to make sure that the file was successfully saved. We are also ensuring that the saved file is not empty. So if the file saving operation fails or the file is missing or empty, we throw an exception. Now, in summary, this method is charged with the responsibility of securely saving an uploaded file and also ensuring that it exists and contains data before proceeding. So let's create another method for getting the total video duration. This method, as you can see here, it uses the FFmpeg probe to get the total duration of a video file in seconds. So here's how it works. The program runs an internal FFmpeg probe command to extract the video's duration. It reads and passes the output and then returns the total duration as a double. Alright, so this method will throw an exception if duration can't be read or passed. This method also ensures the process completes using a wait for in the finally block as exemplified in this code. Now, the wait for method in Java is part of the process class. It blocks or pauses the current thread until the external process represented by the process object has completed execution. In summary, this method is in charge of calling FFmpeg probe to accurately retrieve the total playback time of a video file. Alright, after implementing this method, we need to create a dedicated service called FFmpeg process manager, and then move this method here to ensure proper separation of concerns. Let's also implement another method. This method will handle a video compression using the FFmpeg program. This method is going to be the main logic that will handle a video compression process. Now let's get into it. Right here, this method starts a video compression process using FFmpeg via a process builder. The number of CPU threads for FFmpeg, we have default settings of auto, and we have also specified 28 as a default constant thread factor. Alright, as you can see, we are also setting the encoding speed to compression ratio to medium. Now the progress output is being sent to a standard output pipe, which is one. Now this is necessary for real-time tracking. So this is where we get the details of a video compression process, like in bytes, that will be sending to the front end to actually build our progress bar or construct the progress bar updates. Now the method ended up returning a running process object for monitoring or interaction. In summary, this method is in charge of running an FFmpeg command to compress a video with customizable settings, and also prepares it for progress tracking via standard outputs. The method is also going to be injected into the video compression executor service, where we'll be needing it. Now, we are going to implement another method that will handle the registration of a new background job. So the background job represents the video to be compressed. The video is going to have a unique ID, and then we are going to associate it with the corresponding process. Now, the unique ID will be sent from the client side. All right, so let's dive into the implementation now. So looking at what we have now, this method stores the job in a shared map, which we call active jobs. Now the active jobs map is used for tracking and ongoing jobs. That is to say, videos that are currently being compressed. The method ended up returning a success response confirming registration. In summary, this method will help us keep track of an ongoing video compression process and return a confirmation response. We have also injected the functionality into our video compression executor service where we need it. So after that, now let's initialize a shared thread safe variable to track the current compression progress. This shared variable called progress can be safely updated by one thread, that is when tracking FFmpeg output, and can also be read by another thread or even the WebSocket service. So now we will need to implement some functionalities that will oversee our real-time progress tracking in our video compression app. So we're going to create a dedicated service for this implementation. So let's dive into it. Alright, so as you can see here, we have created a service called Compression Progress Tracker. This service has the sole responsibility of tracking and broadcasting real-time progress during video compression processes using FFmpeg. So it tracks compression by reading FFmpeg output line by line, alright, then passing time values from lines and also calculating the completion percentage. It is also comparing current output time with the total video duration, and it is also updating our atomic reference variable to enable the sharing of progress safely across threads. And finally, we are sending real-time update via WebSocket to the compression progress object, which is going to act as a response object for us here. Now, in summary, this service will be in charge of monitoring FFmpeg's output during the video compression process, and also calculating how far along the process is, and also sending live updates to the connected client via WebSocket. So we have also injected the compression progress tracker class into our video compression executor service. Alright, so now let's move to the next implementation. Alright, so we need to implement another helper functionality that will block the current thread until the compression process completes or the timeout is reached. Now let's quickly implement it. Alright, this is what we have here. This method will wait for the FFmpeg compression process to finish. So we have also set a timeout for it to prevent hanging. If the compression process takes too long, that is more than the specified compression timeout, now this method will wait for the FFmpeg compression process to finish. We have set a timeout for it to prevent hanging. So if the compression process takes too long, that is more than the stipulated 1 hour compression timer that I have specified, it is going to forcibly terminate this program and throw an exception. So in summary, this method will ensure that the video compression process doesn't run indefinitely by enforcing a timeout and doing the necessary cleanup if it exceeds the allowed time. Now we also need to ensure that the program waits for the progress tracking thread to finish before continuing. This is necessary to ensure that all final progress updates to 100% completed and are sent to the client before the method returns a response. So right here, as you can see, the progress tracker thread is responsible for reading FFmpeg's output and also sending real-time progress updates. Calling the join method to ensure that the main thread doesn't proceed to check the results or return a response until compression is truly done. So this is going to help us to maintain proper synchronization between the background tracking thread and the main processing thread. So we are going to have another method that will help us validate the compression results. This method here is going to ensure that the video compression process was successful by checking the results. As you can see here, it checks if FFmpeg exited with a non-zero exit code. A non-zero exit code indicates an error, and the method also tries to verify that the output file actually exists after compression. So if the compression failed or the output file is missing, it throws an exception. In summary, this method is designed to confirm that the video was compressed successfully by validating the process exit code and the existence of the output file. Alright, so we are going to create a dedicated response utility service that will contain our custom response functionalities. So we will also create a functionality that will allow us to generate a structured success response after a successful video compression process. Now, looking at this method, it calculates the original and compressed file sizes. It also computes the compression ratio as percentages and also logs a summary of the compression results. At the end, it finally returns a success response object containing the compression status message, the output file path, and the original and compressed file sizes. And finally, the compression percentage, which we have set to 100.0, which is a double here. So if the compression progress is completed successfully, the progress bar is expected to be at 100%. Now, in summary, this functionality is saddled with the responsibilities of generating a detailed success response with file size metrics and also to log outcome after a successful video compression job. So we are also going to inject this method into the video compression executor service. We need to also ensure cleanup happens every time. Whether the compression succeeds or fails, there should be a cleanup operation. Now, the finally block will contain two methods that will help guarantee that temporary files are deleted and job tracking is cleaned up properly, no matter what happens during video compression process. That is, whether the process succeeds or whether the process fails, there should always be cleanup. We are going to create two helper methods that will handle these cleanup operation processes in our finally block. Now, the first one will clean up any resources or references tied to the job ID if a compression gets completed or fails. And the second method will handle the deletion of any temporary input file created during uploads. Now let's create these methods. Alright, as you can see right here, the first method for cleaning up a job is correctly managing the removal of a job with the given job ID from the active jobs map. So this will help us clean up resources and avoid memory leaks after a job finishes or if the process fails at a point. And like I've said earlier on, the clean up job method we first check if the file exists. It will then try to delete it, and finally it will log a success response or any failure encountered during the process. I'm not throwing any exception here because I don't want the program to break at all. Alright, and also it is very important to ensure that temporary files are properly removed in order to free up space and also keep the system clean. Now, in summary, these methods is going to help us to prevent resource leaks. For example, like a leftover temporary files, memory bloat, etc. So they also ensures that the system stays clean and efficient after each compression attempt. Alright, so we are going to create another class now called video service implementation. Alright, and we'll also create an interface called video service for it. Now, this service will be annotated with a attribute service as it is going to serve as our business logic component. Now, the service will be in charge of providing an asynchronous video compression service using dependency injection and Spring Async support. So let's get into it. As you can see here, this service is currently using our video compression executor service to handle the actual compression logic. So we have created a method called compress video, and we have marked this method to be executed asynchronously. That is in a separate thread from the calling thread. This will allow the main request thread to continue without waiting for the compression to finish. And this is ideal for long-running operations like our video compression processes. So if everything goes well, we expect this method to return a completable future that takes a success response. This response will represent the result of an asynchronous computation. We called the executor service.compress video to perform the actual compression. And if the compression is successful, we are wrapping the result here in a completable future completed future. Then we pass in the response to it. All right, as you can see. So in case of any exception during the process, we return a failed future using completable future.failed future. Then we pass in the exception object. So we have also made sure to catch all exceptions and propagate them properly through the completable future, so that any method or service calling this function can handle all errors consistently. This method is acting as an async wrapper around our video compression logic. So in summary, this service is in charge of wrapping a video compression process in an asynchronous call, also allowing it to run in the background while returning a future result that our clients can wait on or handle asynchronously. Now, our next step will be to create a REST controller class for our video compression service that will handle our compression requests. So we are going to be exposing all the APIs that will handle our video compression processes inside this controller class. So we'll create an endpoint that will handle our video compressions. Let's dive into the implementations. We started by annotating our controller class with athlete cross origin, so which tells our backend to allow our cross origin request from any domain. And here we also use athlete request mapping, which specifies the base path of our server as defined in the application.property config file. Now what will happen is that if we have, let's say we have address like http //localhost 5050, let's say our app is running on port 5050, all right? So what this app.title is going to do is that it is going to append API/v1, which is the version, because we have specified that in the .properties file, all right? So it's going to specify /API/v1, then the name of the endpoint. Let's say we have an endpoint called like compress or upload, all right? So that's what it's going to append to it. So that's what this athlete request mapping annotation is going to do for us. So now we have athlete REST controller, and this is useful for building RESTful web services. So it enables methods to return data directly in the HTTP response body. So we also injected the video service into the controller, which will handle all asynchronous video compressions. And we are then sending a post request, as you can see in this endpoint. Now the method is post, and it's expecting from data parameters such as the video file, which is of course a multi-part file, the file name, and the job ID, which is going to be a unique ID for tracking the compression job. So we are also delegating the video compression responsibility to this our method that is coming from the video service. It's called a video service.compress video, so which we handle all background processing. We then return a completable feature that has a response entity, all right? And this is going to allow for non-blocking response handling. And we are also using exceptionally to handle exceptions gracefully right here. We have also made sure that all errors returned a structured response object, as you can see in the code. So in summary, what we have implemented in this REST controller will handle all incoming video compression requests. So it will also run them asynchronously and then return a structured response, whether success or error, in JSON format. So we have also ensured that there is a proper real-time support for progress tracking via jobs ID and also error handling for client application, and all these are covered in this our implementation. We need to create a functionality that will handle the cancellation of a video compression process. So when a video is being compressed and the user changes its mind, like he wants to cancel the operation, there should be a button in the UI that the user can just click and the video compression process is cancelled. All right, so now we are going to write some implementation that will handle that cancellation in the backend to ensure that when the video compression process has been cancelled, there is proper cleanup and everything is properly handled in the backend. So now let's dive into the implementation. Alright, so as you can see here, this method is going to stop a video compression. So it's going to stop a running video compression job and also clean up all related resources. So here's how it works. When the user clicks on the cancel button, as I've explained already, the job ID will be sent from the client to the server. This method is going to find the job using its ID that was sent from the client from the map of active job that we have defined initially. Remember that Each time we start a job, we are adding the job to an active map, all right, to keep track of it. So now we are going to find the job in the map using the job ID. If no job is found in the active job map, this method will then throw this custom exception that I've just created called active job not found exception, which is going to throw a 404 error, meaning not found. If the job is found, it is going to forcefully stop or destroy the associated processes that is linked to that job. So it will then proceed to remove the job from tracking. And after that, it is going to send a WebSocket progress update indicating successful cancellation. And finally, it will also return a success response confirming cancellation. So, and the front end is going to use this response to construct a custom response that is user friendly to show the user that his cancellation operation or his cancellation request is actually successful. So I want you to also notice that we also created a custom check exception, which we threw when a job with a given ID is not found in active jobs. We also created a global exception handling class, which will centralize exception handling for this application. All these will ensure consistent and user-friendly error handling across our video compression APIs. So in summary, this method will handle the safe cancellation of an ongoing compression task by stopping the processes and also notifying the user via WebSocket and cleaning up all internal tracking data. So having done that, let's quickly expose an API that will handle a compression cancellation request. Now let's dive into it. As you can see, our cancellation API is a post request and the cancellation endpoint is /video/cancel. Then we pass in the job ID. This endpoint will cancel an ongoing video compression job by its ID. The endpoint will take the job ID from the URL path and then call the cancel job method from the compression service to stop the running compression process and also clean up the job tracking, and then send a WebSocket update about cancellation and finally return a success response. So in summary, this endpoint is going to provide a RESTful way to cancel a video compression task in real time while ensuring a clean termination and also providing proper feedback to users via WebSockets. Alright, so this is the end of part 3. I want to sincerely thank each and every one of you who made it all the way to the end of this video. I'm highly motivated by your support, comment and engagement to keep building. In this part, we dive deep into the backend implementations and covered everything related to video compression in the server side, such as setting up essential configurations like WebSocket and CORS, handling secure video uploads, integrating FFmpeg for compression, managing background tasks with multi-threading, and even adding real-time progress update and task cancellation. Basically, we built the engine that powers our entire app. Now, everything is set from the backend side. Our app can receive videos, compress them efficiently, and send back the processed files all in real time. In part 4, we are concentrating on the front end. We will be connecting our beautiful UI with all the powerful backend functionality we just built. So you will see how to handle file uploads from the browser, display real-time compression progress, manage errors gracefully, and tie everything together into a seamless user experience in part 4. I will encourage you not to miss it. Please hit that subscribe button if you have not already done so, and turn on the notification bell so you are the first to know when part 4 drops. If you found this video helpful, go ahead and give it a thumbs up. Drop your thoughts in the comment section. I love hearing from you, and if you know someone who will benefit from this series, feel free to share it with them. Stay tuned and watch out for part 4, where we bring everything together on the front end. And also don't forget that the best way to learn is by doing. So until next time, keep building.